We've done the heavy lifting, and we've slogged through some pages of long equations. And, truth be told, the results haven't been that exciting. But that was yesterday. Today's a new day. And while we will see a few long equations in this video, they will be ones we've seen before, so we'll greet them as old friends. And this time around, there will be some interesting, we might even say exciting, results. So, let's get started. This page recaps the results from the first three videos. We have the physics of heat transfer, Fourier's heat transfer law, and the relationship between temperature and heat energy. And we have the differential equation model for 2D heat transfer that we derived in the previous lesson. Starting with the differential equation model, we make the FDM substitutions for the derivatives in the model, giving us equation 1. We solve equation 1 for temperature at time t n plus 1 at the ij grid point in terms of the grid point temperatures at time tn, giving us equation 2. And with dx equaling dy, equation 2 simplifies to equation 3, which is the computational equation we'll translate verbatim to MATLAB to compute solutions. And we'll consider the same system as the first example in the previous video, except that this time we'll compute changing temperatures. So we have a 3 by 3 meter thin plate and a 4 by 4 grid with the temperature at the top edge of the plate held fixed at 100 degrees and the temperature at the bottom edge held fixed at 0 degrees. We specify Neumann boundary conditions for the left and right edges as indicated by the equal signs, requiring that the spatial derivative of temperature in the x direction be 0 on the boundary. The equations for the boundary conditions are identical to the ones we specified in the previous video. Here is how the calculations look done by hand. It is essential that you fully understand how the calculations are done by hand before writing a program to do them. So make sure that you are comfortable with every detail of the calculations for the interior points and the calculations for the points with Neumann boundary conditions as shown on this page. The program has some new features, so we'll look at it in some detail. First, we initialize Kc, which I should have named Kdc, as it has the value K divided by C, and Nx, the number of grid points in the x direction, and Ny, the number of grid points in the y direction. We initialize a two-dimension t-array for the calculated temperature values, and we initialize constants dx, dy, dt, and capital N, the number of time iterations. We initialize the non-zero Dirichlet boundary conditions. And then we graph the initial temperature profile. MATLAB automates this for us with the built-in function surf for surface. Note that the argument to surf is t transpose and not just t. This is necessary so that the graph will match our grid layout. Here we have the computational loop for computing t at time t n plus 1. Note that the computational equation for temperature at time t n plus 1 has on the right side of the equal sign values of temperature at time t n. So it is necessary to save the temperature values at time tn before calculating the values at time tn plus 1. The statement tn equals t does that. Next, we sequence the index values I and j through all the interior grid points, but none of the boundary grid points. Hence, the limits on the for loops are 2 to nx minus 1 and 2 to ny minus 1. Next, we have the computational equation derived from the differential equation model translated into MATLAB. The inner loops compute the values for the interior grid points. No calculations are necessary for Dirichlet boundary points. However, the Neumann boundary values must be calculated, and this time we want temperatures at time tn plus 1 on the right side of the equal sign. Finally, we animate the process. That is, we graph the temperature profile just calculated and pause the program for half a second. The result should look like following. There are two assignments. The first is to calculate the time-dependent temperature profiles for a 9 by 9 plate with a 10 by 10 grid with the following boundary conditions. 0 degrees along the bottom edge, 5 degrees along the top edge, and also with the temperatures at grid points 5,7, 5,8, 6,7, and 6,8 pinned at 10 degrees. The code outline follows. Assignment is to calculate the time-varying heat distribution in a 19 by 19 plate with a 20 by 20 grid with the following boundary conditions. The bottom boundary held at 0 degrees, the top boundary held at 250 degrees, and the sides with the usual Neumann boundary conditions. And in this problem, we add heat sources of 100 watts per square meter at grid points 5, 5, and 10, 15. The computational equation is shown at the bottom of the page, and the program modifications necessary to incorporate the heat source follow. The second